All right, in this video, we're going to take a look at how do we actually compute minimum sample size requirements to build the kind of interval that we want when we're estimating an average. Again, all of this information is also listed on the formula sheet right down here, minimum sample size. We'll notice that this is a very different formula than what we used when we were estimating for percentages. So we have to be aware that when we're asked for a minimum sample size, we need to be careful as to whether or not we're being asked to work with a p or whether we're being asked to work with a mu, a percentage or an average. This average size is actually a little bit easier because we won't have any weird selection of a p star in this formula, which is very, very convenient. We will still have our ZC, which you'll notice has the exact same formula, and the N formula is kind of comparable. We just have an S that's multiplied in, and then no extra p stuff on the side. Let's take a look at how it works. Okay. I've summarized all the same stuff up here in the box. Let's just jump in right to example 4. A sample of 20 cars shows that the sample standard deviation of the miles per gallon is 2.5. Okay. How many test runs of an automobile would be required if I wanted to determine the average miles per gallon rating on the highway to within half a mile per gallon? So here I'm being told in error how far I'm willing to be above or below by with 95% confidence. Okay, so I'm going to write down all the information that I already have here. I have an error of 0.5. Notice I'm told at the beginning of the problem that there's a sample standard deviation of 2.5. I have a level of confidence of 0.95. And so my ZC, according to what I have up in the box above, can be found with an inverse normal of a 1 minus a 0.95, all chopped in half. So let's see, 1 minus 0.95 is 5%, and 5% chopped in half is 2.5%. Okay, great. This is all the information that I need to fill in the formula. So N is going to be equivalent to taking this inverse norm, multiplying it by 2.5, dividing it by 0.5, and then squaring the entire result. I'm going to go to the calculator to figure out exactly what this is. Here we go. I'm going to start with my inverse norm, 0.025. 0, 1's already in there. This is great. Multiply this by 2.5, divide this by 0.5, and square the total result produces an amount of 96.0365. Now, I of course want to ask here, 96.0365 what? And in this question, it's not like I'm working with people, I'm not talking about TVs. In this case, I'm talking about how many test runs of an automobile. So I need this many test runs, right? I got to do that many test runs. Of course, I can't do that many test runs because that's a decimal amount, so I have to round up. And N then would have to be 97. Notice I'm always rounding up again because this is the minimum I can have. I can't go lower than that, so rounding down isn't an option. I must round up. So I'm going to have this many test runs. Perfect. I'd like you to go ahead and see if you can try to do the exact same thing here on example number 5. Notice though, be a little bit careful, you are told that there's a small sample of bulbs that shows that the variance is going to be equal to 5,625. So you think carefully about that as you begin to set up this question. Pause the video, really see what you can come up with, and then of course unpause when you want to see the solution. Okay, so here's what we have. The lifetime of a particular light bulb is going to be tested. A small sample of bulbs shows that the variance of the sample lifetimes is 5,625 hours. What is the minimum sample size required if we want to estimate the overall average lifetime? Okay, so let's see. I want to estimate that overall average lifetime to within 10 hours. So it seems like my error is 10 this time. I'm told that my sample variance, which is S squared, is equal to this much. But of course, that means I need to find what S is. But an easy way to go from a value of S, to a value of, or from a value of S squared to a value of S would be to take this value of the 5,625 and square root it. And if I do that, I get 75. Then I also have my level of confidence, which is 90%. And my ZC then is an inverse norm. If I plug everything in here, I should simplify down to 5%. And so then I get the following setup. This inverse norm times 75, divide by 10, and square the whole result. When I crunch that on the calculator, I get the number 152.1868. Of course, I can't with that, so I need to round up. And that gives me a final answer of 153. The units on this, though, is important. And my units here should be light bulbs. This is the number of light bulbs that I need to test. Okay, hopefully you got the right answer here. If not, there are plenty of more problems in the worksheet that you can try to go practice with. Again, hopefully this feels very similar to what we actually did on the other side of the formula sheet, and that left column where we did this with percentages. Although I think this one is a little bit easier since there's no P star to try to go ahead and figure out. Okay. In the next video, we'll take a look at something we also did last time, which is, or by last time I mean last section, which is hypothesis testing using confidence intervals. And we'll kind of see how that process works in this side of the formula sheet as well. Okay, I'll see you over there.